this nice introduction, and welcome and good morning to all of you who are here so early. Today I would like to introduce you to our work which we have done over the last years on Kesterite semiconductors, especially focusing on crystal structure and structural properties. So let me start with showing you these two efficiencies, which I have taken, of course, from the NREL chart. It's only showing two lines of these many lines in the NREL chart, which are for copper, indium, gallium selenide based thin film solar cells, the green line, and the red for the copper, zinc, tin, selenide, the Kesterite solar cells. So you know that these thin film solar cells are called second generation of solar cells, silicon PVs first generation, and the thin films is the thin film technology is called the second generation. So if you look for the cross sections for Kesterite solar cells, so this is the absorber layer, or here for the copper, indium, gallium selenide, at the first view they don't look so much different from morphology. But the efficiency, there is a big difference. The chalcopyrite-based solar cells are above 22%, but the Kesterites stick at 12.6, and you may ask why it's not increasing over the last years. It's still the world record from Theo, who will speak later after the break. So the main problem in Kesterite-based solar cells is discussed as the VOC loss. So it's a loss in open circuit voltage. If you look for this IV curve here, you see two lines, one for a chalcopyrite solar cell and one for a Kesterite solar cell, and you see especially here in VOC there is a big difference. GSC is not that bad, but the VOC. Also, if you look for the EQE measurement and comparing not that good chalcopyrite solar cell, 15% with an 11% Kesterite, you see that you have first a broad PL here in the Kesterite, and you have a difference between the band gap and the PL, peak maximum, in the Kesterite. So this is interpreted as fluctuations, which can be band gap fluctuations in the absorber, which are due to structural disorder, and it can be also electrostatic potential fluctuations, which are due to charge point defects. You also see this tailing due to these fluctuations. Here in the EQE you have a strong tailing for the Kesterite, and this suggests that you have a high density of states in the band gap. So in the first part of my talk, I would like to introduce you to the Kesterite-type compound semiconductors, which is a complex material, and I will show you which structural disorder we can have in that material. In the second part, I will show you our experimental proof of this model I will develop in the first part. So the Kesterite is a quaternary compound, more complex than the chalcopyrites, which are a ternary compound. Even if it's copper, indium, gallium selenide, it has 4 elements. It's a ternary compound because it's a solid solution between two ternaries. But here we have a real quaternary, so we have to deal with this quaternary phase diagram, copper, zinc, tin, sulfur, or selenium. And the Kesterite you can find in a cut in this triangle here between copper sulfide, tin sulfide, zinc sulfide. Of course, you can make other cuts, but we always choose this one. And this is the Kesterite-type structure, which is known already. The name comes from the mineral Kesterite, because there the structure was determined first time. The mineral is copper, zinc, iron, tin sulfide, so it's a mixture of zinc and iron. The structure is tetragonal, and we have layers of, this way, once more. We have layers of copper and tin, copper and zinc, copper and tin, copper and zinc, and so on. If you look in these layers perpendicular to the C direction. So these are the Wyckoff positions, 2A for copper, 2C for copper 2, then the position 2D for zinc, and the position 2B for tin. These Wyckoff positions are according to the space group, which is I4 bar for Kesterite. So all these compounds here named crystallize in that structure. So the absorber in the thin film solar cell has an off-stoichiometric composition. That means it's not 2 to 1 to 1 to 4. It's like in chalcopyrite thin films, copper poor and zinc rich, or copper rich and zinc poor, or you have other possibilities. So the formation of the off-stoichiometric compound goes along with the formation of intrinsic point defects, the same as in the chalcopyrites. So there are so-called good defects and bad defects, which you can see here from this from literature. There are calculations about defect levels in the band gap for all the different types of defects which you can have in the Kesterite. So these defects are acceptors or donors. They can be shallow or deep. And shallow defects are copper vacancies and zinc on copper, and the most others are not so favorable. As you can see here, copper vacancies are shallow, also zinc on copper is shallow, but all the tin-related defects are not that nice. You see they have states in the middle of the gap. So how to make Kesterite off-stoichiometric? So first you start to think within the phase diagram. It is copper sulfide, tin sulfide, zinc sulfide, same is for selenites. And you can define the cation ratios, copper over zinc plus tin or zinc over tin. And both ratios can be smaller or bigger than 1. Then you have an off-stoichiometric composition. So you have all these possibilities here to deviate from stoichiometry. So first, we choose this so-called, we call it cation ratio plot, to show these different possibilities of off-stoichiometry. So you have this 4 different parts. Of course, in the middle you are stoichiometric, and if you go in this way, for instance, you are copper rich, copper poor and zinc rich. So in this way we can define a copper poor region, or on the other side, a copper rich region. So now, if you go away from the stoichiometric point in any direction, you form an off-stoichiometric Kesterite. But this should be a little bit more in an ordered way. And so, let's say we go from the stoichiometric point in this direction to a not existing compound zinc to tin S4. And then you would go along that line in the cation ratio plot. So some years ago, Alain Lafont suggested a so-called cation substitution model to form an off-stoichiometric Kesterite. So what you are doing, if you go along that line, in principle you form a solid solution between the stoichiometric Kesterite and this not existing compound. And this is the cation substitution you have to do in this solid solution. You replace 2 copper by a copper vacancy and a zinc. So that means if you look in one of these planes here, you have copper and zinc and tin. This is this plane and that plane looking in this C direction. First you take the copper out to form a vacancy, and then you take another copper out and place a zinc on that side. So in this way you form copper vacancies and zinc on copper, and you form an off-stoichiometric Kesterite with this composition and copper vacancies. So this is the way he introduced, Alain Lafont introduced, and he calls that A-type. So he started with the first letter. So now you know that this line is the so-called A-type. It's an off-stoichiometry type called A. In the same way I have shown before, you can define many other types, and we ended up to L. So we have A to L, all different off-stoichiometry types, and each type is connected with a special cation substitution, so that you can, these are not all, only a few, are shown here, that with each off-stoichiometry type you have a special chemical formula. This was the A-type line, the black one I have shown you before. So you have different off-stoichiometric types in copper-poor zinc-rich, copper-rich zinc-rich, and so on in all the different regions. And with each off-stoichiometric type, there are certain point defects connected with. As for the A-type, this line, copper vacancies and zinc on copper. The red line is the so-called B-type, zinc on tin and zinc on copper. You see, you are copper poor, but you have already no copper vacancies anymore. If you go in that way from the A-type to the L-type, you have tin on copper, zinc on copper, and a lot of copper vacancies. So that means in this way you can define existence regions for point defects, and here in blue I have marked existence region for copper vacancies as an example. You should keep in mind that these copper vacancies are responsible for the p-type conductivity of the material, so it's important that we have them in the Kesterite absorber layer. So this is a model, and now we have to think about how we could prove this model experimentally. For that, as we always do, we study this intrinsic point defects by neutron diffraction, and I will explain you why we have to use neutrons in the next slide. So if you do a diffraction experiment like X-ray diffraction, electron diffraction, neutron diffraction, your intensity, what you measure in your detector, is proportional, I was too fast, is proportional to this structure factor F HKL. So for the diffraction on each lattice plane, you can calculate this structure factor. And this is the formula for the structure factor. So you have the HKL values, which are the Miller indices of the lattice plane where you diffract your X-rays or neutrons. X, Y, Z is the position of your atom in the unit cell. And this little f is called atomic scattering factor. This defines the strength of the atom you have for scattering of X-rays or neutrons. So if you look for the scattering factor for copper plus and zinc 2 plus for X-rays, this is the little f, you see there is not much difference. So if you now evaluate your data and do a Rietveld analysis, for instance, it's difficult to distinguish between copper and zinc because the scattering power is nearly the same. And if you use neutrons, then you have here the same formula, only this factor which defines the scattering power is different. This is called a neutron scattering length. It's with a little b, its name. You can look up that in tables. And you see the neutron scattering length for copper and for zinc. And there, you see there is a big difference in between. So if you use neutron diffraction, you can distinguish very well between copper and zinc in your crystal structure. And this is important because you see you have, according to the definition of the Kesterite-type structure, you have an ordered distribution of copper and zinc. So with neutron diffraction, you can distinguish between isoelectronic cations, in our case, copper and zinc. You also can, if germanium comes into the game, you also have to distinguish between copper, zinc, and germanium because they are also isoelectronic cations. Or if you think on minerals, aluminium and silicon, they are also isoelectronic. So if you would like to distinguish this, neutrons are a good solution. But for this, you need a large sample volume if you would like to do neutron diffraction. And then you get powder data. And we do Rietveld refinement from which we get the cation cytocurrencies. And from this, we deduce the point defects type and concentration. So it's a qualitative and quantitative result on the point defects which we get. But we need a large sample volume, so we cannot do this on thin films. We synthesize powders by a solid-state reaction, which is shown briefly here. And then the first step, what we are doing is we determine the chemical composition of what we have analyzed to look if we really have a Kesterite and how homogeneous is our powder. So for a requirement to do a neutron diffraction data analysis in the way we are doing is that we have a homogeneous powder. That means only one quaternary phase with a homogeneous composition. We can have secondary phases, this is not a problem, but the quaternary phase should be only one. So you see here these gray grains are all Se2 in this case. It's a sample with these cation ratios. So we determine the amount of the elements and we have internal standards in this standard set for the WDX spectroscopy. And so we can very nicely calculate for each of our samples this cation ratio. And we also can determine the secondary phases. This is an example of the Se2 powder samples we have synthesized in between A-type, B-type, and G-type, which is not shown here, line, and also in the copper-rich region. And with the color, there are marks the secondary phases which are formed. We also get some off-stoichiometric single-phase Kesterites, which are shown in red here. So each point you see here is one sample. And each sample contains only one Kesterite phase, as for instance, the sample shown here contains this off-stoichiometric Kesterite and tin selenite, so because it's green here. Then we do the neutron diffraction experiment. We measured a lot at the research reactor in Berlin, but also at, in Oak Ridge at the SNS, the spallation neutron source. Then we do the Rietveld analysis of the data. That means it's a full pattern refinement. You have to put in a starting model for your structure. So we use the Kesterite-type structure as the starting model. And then you refine the parameters. So it's a structural refinement, not a structural determination. Then we get the lattice constants, the cytoccupancy factors, temperature factors. These are the factors corresponding to the structure, and then you have all the global, like peak shape, background, and all the other things. And we include the secondary phases, which we know from WDX analysis. Here we show two examples of two off-stoichiometric Kesterites. This is the refinement. So the first line here, these are the bragg peaks of the Kesterite phase, and in the second line you see here a secondary phase, which in this case looks like zinc selenite. And here, this looks like tin selenite. This is another secondary phase in this sample. So most important for us are the cytoccupancy factors. So we work with them to calculate what we call average neutron scattering length. So from the Rietveld analysis, you have your cytoccupancy factors of your 4 different cation sites. Of course, also for the anion site, but here we look for the cations. And from table, you know the neutron scattering length of your elements. So you put this together and you calculate the experimental average neutron scattering length, taking the cytoccupancy factor from the Rietveld refinement and multiply this with the neutron scattering length of the element which should be on that site according to the Kesterite crystal structure. So you get the set of experimental values. On the other hand, you have your cation distribution model, which I showed you in the first part. There are specific point defects according to the off-stoichiometry type. From the chemical composition, we determine the cation ratios. So we know the off-stoichiometry type of our sample, of our Kesterite phase in the sample. And then we calculate from a cation distribution model the so-called calculated average neutron scattering length. So we take a distribution of copper, zinc, and tin on these 4 different positions according to the model. And of course, we have to take care for 2 additional requirements. We assume that each cation site is fully occupied. So we also include vacancies in this model. And also, the sum of the cation spaces which are distributed on the cation site have to be that what we measured by WDX. Of course, we cannot distribute more than we have, and everything what we have measured should be distributed. So in that way, we compare this experimental and calculated average neutron scattering length of the cation sites. This is just an example to show you how it works. This is not measured. This is just to show the principle. If you have Kesterite-type structure, you have this cation distribution. So you have copper on 2A and 2C side, zinc on the 2D side, and tin on the 2B side. And your experimental average Newton scattering lengths, which are the dots, this is the average Newton scattering lengths, and the 4 sides should be on the lines for the copper sides, for the scattering lengths of copper, for the tin sides here on that line, and for the zinc side on that line. And then if you calculate according to this cation distribution model, this scattering lengths, then the calculated values will be on the same point as the experimental values. I can tell you we have never seen something like that in none of the sample. So we started with stoichiometric material long time ago, and we measured something like this. So for the 2A side, the experimental value is nicely on the copper line, and also for the 2B side, the value is on the scattering length of tin. But for the 2C and 2D side, we found an increase of the average Newton scattering length for the 2D side and a strong decrease on the 2C side. So they showed values which are in accordance to a 50-50 statistic distribution of copper and zinc on 2D and 2C. So, and that's why this was named disordered Kesterite. You always have that in these planes. So in these layers here, this layer and this layer in the crystal structure, you have a lot of antisides, and you have a disordered distribution of copper and zinc. You can change the degree of disorder according to your gross temperature, and if you take a long time, it will be a bit less disorder, but to reach complete order will take, I think, years. So we looked for the order-disorder transition also, I will not show here, but to reach order by long-term annealing takes a very long time. So what to do to get rid of this copper-zinc disorder, which will give rise to these tail states, and this, we don't want to have it. So we tried to substitute copper by silver, to reduce copper-zinc disorder. So these are, this is the copper-silver content and lattice parameters, and we synthesized these 3 samples, mixed crystals between copper and silver, and this is the copper end member and the silver end member. Both end members crystallize in the Kesterite-type structure. They are a bit off stoichiometric, but only slightly, as you can see here. They are all A-type, between A-type, B-type, and G-type. So a little bit of stoichiometric only. So we did the neutron diffraction experiment, and this is the cation distribution we determined experimentally. So on the 2A side now, there is no copper anymore. It's all the zinc is on the 2A side. On the 2C and 2D side, you have copper and silver. Of course, they should share a side. And on the 2B side, you have the tin. And now this is not the Kesterite-type structure anymore. This is another structure which is shown here, and this is the stannite-type structure. So for the alloys between copper and silver, at least for these 3 we have investigated, they show clearly stannite-type structure. That means copper and silver share these positions here, and you have no copper-zinc disorder anymore. Unfortunately, we form a secondary phase which has a low band gap. This is silver 8, tin, selenium 6. It has the argyrodite-type structure, and this group of materials is well known in thermoelectrics, especially with copper instead of silver. So then we measured this absolute photoluminescence hyperspectral imaging, from which it is possible to deduce the external PL quantum yield, EQE-PL, and is shown here. With the silver, content increasing, and this is the EQE, and this is increasing. With this, you can determine the quasi-Fermi level splitting, and this allows you to estimate the maximum achievable VOC in a solar cell. And you see that with increasing silver content, you increase your VOC and you decrease your VOC deficit. So this is the VOC according to Schoch-Sequeisser limit, and this is the VOC we determine in the powder. And this is very nice what you could get in the bulk material. So unfortunately, the papers about the thin films, they are not that good. Okay, I have to speed up. So in principle, silver incorporation is very promising to increase the VOC and reduce the deficit. One view to the off-stoichiometric Kesterite. Now in off-stoichiometric Kesterite, we do the same analysis. We determine this average Newton scattering length experimentally, and we calculated it according to the cation distribution model. This is the cation distribution model. This is a AB-type Kesterite, so copper poor, zinc rich. And you see now you have copper vacancies, zinc on copper, zinc on tin, defects, and you have always copper-zinc disorder. This is another type. This is a GF-type Kesterites, a series of 10 samples. This is the cation distribution model for these 10 samples. You see now you have no vacancies anymore, but you have copper on, this is in germanium, copper, zinc, germanium selenide. You have this anthracite zinc on germanium, and you have always copper-zinc disorder. From this we can calculate not only the side fractions of the different defects. These are just 3 examples shown here. We also can calculate the concentrations for these 3 examples shown here. Copper vacancies, zinc on copper and zinc on tin. And you see the concentrations are very high. This is just from the structural origin. Of course, they are not all electrically active because it's possible to form defect pairs in the same, this is the same model which is applied also in the chalcopyrites. You form defect pairs to make this structural point defects inactive. But you have to think, besides this point defects, you have always copper-zinc disorder. So now we know that this model proposed from Alain Lafont to define off-stoichiometry types can be applied to Kesterite-type compounds. And we know now the existence regions of the different defects. Some are shown here. On this left side, the shallow defects, and on the right side, the deep and mid-gap defects, which should be avoided. So in principle, now it's possible to determine from the composition of your Kesterite phase, you can expect what defects you will have in your thin film. But it's very difficult to determine the composition of your Kesterite phase in your thin film because you have also the secondary phases, and you will always measure an integral composition of the whole film. Now you can think about what would be the recommended growth region for your thin film. So you have to avoid deep and mid-gap defects if possible. So, and I think it would be good to have only A-type. So you have copper vacancies and zinc on copper. These are both shallow. But if you would like to have more copper vacancies, you should go in this area more to the L-type. And if you go in this area, so A-B-type mixture, you will have less vacancies. Just to remind you on the defect diagram here. So A-type or AL or AB-type mixtures would be, I think, a preferable region to grow your thin film. So I'm almost at the end. I would like to show you today that the Kesterite type structure is very flexible. It tolerates really large deviations from stoichiometry. I haven't shown you how far you can go because this would add more slides. The stoichiometric and the off-stoichiometric compound crystallizes in the Kesterite type structure, but you have always copper-zinc disorder, so that's why it's called always disordered Kesterite. The copper-zinc disorder correlates with a PL shift. I haven't shown you that, but I can tell you, and this gives rise to bandgap fluctuations. So if you substitute copper for silver, Then you get a material crystallizing in the standard-type structure, at least between 15 and 46% silver. And you have no copper zinc disorder, but you have another secondary phase with a low band gap. But maybe you can edge that. There are recipes to do it. The off-stoichiometric Kesterites can have different cation ratios. And with this, you have various types of point defects and secondary phases. We can apply the off-stoichiometry type model, types between A to L. And now it's possible to predict the occurring point defects from the cation ratios if you can determine this from your Kesterite phase. So with this, I would like to thank all the people who contributed to this work from my department, the Neutron diffraction instrument responsibles, and a lot of cooperation partners, our former EU project, KESCELS, which was very nice, and our new one, Edgardo is coordinating also Infinite Cell. And just to tell you, there are 12 partners in the Infinite Cell project, and 2 are from Morocco, shown here, Maskir and the university, and I would like to thank you for your attention.